Hey everybody, so this video is going to talk about the second lesson in the set theory unit. This is going to talk about intersection and union of two sets, and we're going to be doing a lot of work using Venn diagrams in this lesson as well, so we're going to take a look at that. But first, what is the intersection, what is the union when we are talking about two sets? So the intersection is basically the elements that belong in both sets. They are common to two or more sets. So the key word that you're looking for is the word and we write it like this: A with an upside down U and then B. So what this means is things that are in A and B. Okay, that's what that terminology means. When we talk about the union, those are the things that belong in at least one of the sets. So they can belong in one, or they can belong in the other, or they can belong in both. So the union, that is the word or, and that is the terminology for that. It's A with a U and then B, the U for union. So what this means is A or B. It has to be in one or the other. It could be in both, but it doesn't have to be in both. There is one more, I guess, definition, terminology, whatever you want to call it. A with a backslash and B, that means A minus B. And what that means, those are the things that are in A but are not in B. So in these Venn diagrams here, it says it's the red region, but we're dealing in black and white in these books. So I'm going to highlight to show you what it looks like. So for this first one, we have A and we have B that is fully enclosed in it. So B in this case is a subset of A because it's fully enclosed in A. So the things that are in A but are not in B would be this section here. Basically everything that is not in that B circle. For this one here, these two are disjoint, which means there's no overlap. They have nothing in common. A minus B is just A. It's everything that is in A because there's no overlap, so there's nothing that could also be in B. So in this case, it is just A. And when we have A and B where they have some kind of intersection, A minus B is just, again, the stuff that is in A, but is not in this overlap section. So it is not in this like little sliver here where they cross each other. All right, so we're going to take a look at three examples that are they focus more on intersection and union, not so much on the A minus B part. So the first example says, given the following situation. So my universal set, the stuff, the world that we're working in, are positive integers that are less than 10. So what are positive integers? Well, they're just 1, 2, 3, blah, 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 all the way up to 9. And then we have these subsets. So A is the numbers from 2 to 6, and B is the even numbers of U. So my even numbers from 1 to 10 are 2, 4, 6, and 8. And you can see that there is some overlap between each of these different sets. So what we are going to do is we are going to determine what the intersection of A and B are. What do A and B have in common? Well, we can just look because we have listed them here. So what do A and B have in common? They each have a 2, they each have a 4, they each have a 6. All right. If we were to draw this situation in a Venn diagram, well, we're going to take a look at what that looks like. All right, so the way that we draw basically a Venn diagram is it's always enclosed in a box. The box is my universal set, and then we have our A, which is going to go in one circle, our B is going to go in another circle, and we know that there's going to be some overlap because we have already found the overlap. But now let's go ahead and put these numbers where they belong. So first of all, I'm just going to highlight wherever they overlap. So this section right here, that is my A and B. That is my intersection. So the answer that we already found for the overlap is going to go here in the middle. And apparently my pen is dying. There we go. Okay, so because 2, 4, and 6, those are the numbers that A and B have in common, those are going to go in the middle because that is what they have in common. Then on the A side, we're going to put the numbers that are not in the intersection, so 3 and 5. And on B side, we are going to put the numbers, again, that are not in the intersection, but are a part of B. So the only one here is 8. And then all of the other numbers, keep in mind we have these ones in the universal set that don't go in A or B. They don't fit in either of those boxes, but they do still fit in the box of the universal set. So they're just going to be floating around somewhere in the box out here. So we haven't put 1, we have 2, 3, 4, 5, 6, we haven't put 7, there's 8, we haven't put 9. So these numbers, again, they're still part of the universal set, but they are not part of A and B, so they just go in the box, but outside of the circles. All right, example number 2. Now we have 4 different sets inside a universal set called S, and we can see that A, B, and C do have some overlap to them. In fact, right here in the very middle, this is where all 3 of them overlap. Then we have D that is disjoint from A, B, and C. It's not a part of A, B, and C, but it is still part of S. And if you just look at the numbers here, it looks like S is maybe the set of numbers or the set of integers from 1 to 13. It's not very clear what these sets are. They're not well defined, but we can still answer these questions here. So the first one, the intersection of A and B. So A is here, B is here, and they intersect right here. Okay, so this is A and B. So what do they have in common? They have 7 and 9. A or B. So this one was A and B. This one is A or B. So it's just that whatever numbers are in A or whatever things are in A, or they can also be in B. So we're just going to list the items that are in A, list the items that are in B, and that's pretty much it. So A has 1, 3, 7, and 9. And B has 2, 4, 7, 9, and 10. But we've already written 7 and 9, so we don't have to worry about that. We can just write down the additional numbers, so 2, 4, and 10. Then we have B and C. So B is right here, C is right here. I'm going to highlight this one in orange to kind of separate it. So this is B and C. This is my orange one. So B and C is 1 and 9. Then D is B or D. So they either have to be in B, and I'm going to use yellow for this, or D, which is right here. So this is going to be my yellow. And again, we're just going to list all of the things that are in B and list all of the things that are in D. So in B, we have 2, 4, 7, 9, and 10. And in D, we have 11 and 12. A and D. So A is right here, D is right here. There's no overlap between them, so there is nothing in A and D. So that is the empty set. And the reason why it's the empty set is because A and D have nothing in common. Nothing in common. All right, we have 2 more here. This is A or B and C. So the things that are in A or B doesn't matter, but they also have to be in C. So another way that you can think about this is the things that are in A and C, or the things that are in B and C. Okay, this actually has a name for it. I can't remember what the name is, but there's like different laws that they, I can't remember what the name is. So we're going to consider each of these. So A and C is right here in orange, it is 1 and 9. B and C, I'm going to draw it here in, well, I don't have to draw it in blue, but there's 9 and 10 that are in B and C. So in this case, this is going to be 1 and 9, and then also the 10 as well. And we have one more, which is not A and not D. Okay, so this last one here is not A and not D. So we're going to write down all of the things that are not in A and not in D. Well, D is by itself, so we can just automatically take those out. Then we also have the things that are not in A. So A is right here. Everything not in A is in one of these sort of areas here. So we have 2, 4, 10, and 13. But there are also these extra numbers that are floating around here in the universal set that are also not in A or D. So we have to also include those. So also 5, 6, and 8. There is one more example here, which says Morgan surveyed 30 students in her class. 18 students eat breakfast. 5 of those 18 also eat lunch. 3 students do not eat breakfast or lunch. So how many students actually eat lunch? So again, we are going to create a Venn diagram here. You don't have to, but it is, I mean, there are going to be questions that have Venn diagrams, so I feel like it's better to get the experience of making them and just understanding them, but they are not necessary for, it's not necessary for this question necessarily. Okay, so I have 2 circles here. The reason why I have 2 circles is because we are considering students that eat breakfast and students that eat lunch. And we know that there is some overlap because we know that 5 of the 18 students eat breakfast and eat lunch. So that is going to be my overlap, is going to be 5 students. Then we know that 18 students in total eat breakfast. We know that 5 of them also eat lunch. So that means the remaining 13 are going to only eat breakfast. They are not part of the lunch group. We also know that 3 students do not eat breakfast or lunch. So there are 3 students that don't belong in either category. They're still part of the class. So we can call this set the universal set C for the class. We know that 3 students in the class are not part of the breakfast group or the lunch group. And then the question is, how many students eat lunch? Well, we know that there are 30 students in total. So 30 minus the 13 minus the 5 that eat both minus the 3 that are on the outside. That's going to tell us how many students are in the just lunch group. So 30 minus 13 is 17, minus 5 is 12, minus 3 is 9. So there are 9 students that just eat lunch, but we also have to consider the ones that eat breakfast and lunch. So the number of students that eat lunch is equal to the 9 that just eat lunch plus the 5 that eat both meals, which gives us a total of 14 students that eat lunch.